Okay, hopefully we can finish it a bit quick today. Basically, what we start discussing on Monday, we were start discussing very basic properties of a tree, right? Which we all know even before this course. Just formal definitions of what they look like, and some of the terminologies like tree degrees, height, and depth and length, depth and heights and stuff like that, which you guys all know anyways. But we just looked at it, so we can use those properties to use those measures to describe some of the properties of a tree, or we take a look at the binary trees and etc. So tree, what they look like, and let's go over some of the binary tree properties. Binary tree, a finite possible empty collection of a element. 다 오면 해야 되겠다. I don't want to repeat myself again. Okay. Assignment is due today. So totally forgot about that. So I guess I will put up the assignment solution as soon as possible, sometime this week. I will put up the assignment 4 right away, again this week. So you can give it to me within 2 weeks or so. So I'm guessing again, I think there's going to be assignment 5 this term. So until end of the December, yeah. There should be assignment 5 as well. So look forward to receive your assignment 3, and I will give you assignment 4 right away. Okay, so binary tree, a finite, a possibly empty collection of elements. What was the difference between the just tree definitions? Said, I think in the tree definition, general tree definition, they said non-empty collection of the elements. So it cannot be empty, but here binary tree, possibly empty collection of elements. A non-empty binary tree has a root, non-empty binary tree, so has to be at least one node, which most likely to be a root element, and the remaining elements, if any, are partitioned into a 2-binary tree. One of the very obvious properties of a tree, if you divide a tree, it's still going to be another tree, right? So subtree of a binary tree will be a binary tree, which means they would share the exact same property of a binary tree itself. 그죠? Just apply to pretty much every other trees as well. So they are called left and right subtrees of the binary tree. Left and right binary tree only has two branches from a single node, single elements, right? So that's a quite obvious properties that we looked at before. And difference between binary tree and just general tree, I mentioned. No degree of 2, and difference. Binary tree may be empty, trees cannot be empty, right? That's what we discussed last class. And subtree of binary tree are ordered, or those of the tree are not ordered. ABC, ACB. So if you want to make a distinction between those two, you can take a look at as a one being sorted as a binary tree, the other one as a just tree with a degree 2, no degree 2. Okay. And then we can take a look at it. I mean, blah, 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 blah. And I think when we start discussing the tree, I mean, it's all the basis for your compilers too. When your computer try to read your programs, they have to understand what they each mean like, or what they actually look like. So tree is probably the basis for those compilers who parse those syntaxes, parse those words, and whether to find out whether they comply to the syntax of the certain programming languages that you're using. Stuff, expression tree. And then there was a three binary tree properties. Hopefully, you guys take a look at those proof on the pages 426 and 427, right? 봤겠지? So in 2 days, hopefully you guys take a look at examples, the proof there, in order to prove these three properties. But if you so lazy, didn't look at it, then it's probably the pictures that you might want to remember is like extreme cases or full binary trees like this. Using this, you can actually prove some of it, nicely. Let's take a look at the properties again. Drawing of every binary tree with the n elements n greater than 0 has exactly n-1 edges. Obvious, 그죠? n-1 trees. A binary tree of height h is greater than equal to 0, and at least h and at most 2 to the h-1 elements. You have the height of the tree is h, then at least h. 이거 뭐야? 한 줄로 돼 있으니까 one line, so you might need at least h tree, or if it's like a full tree like this, at most 2 to the h-1. 그죠? 녹으니까. I explained this last time as well. So hopefully do take a look at these properties. I may ask you this proof in your exams too. I can ask you. It's an easy proof to just to follow. Likewise, the height of the binary tree that contains n elements n greater than 0, at least log n plus 1, and most n, see proof. It's the same case on those two cases combined. I don't want to go into this. We discussed good enough last time. So these three properties, it's reasonable for me to ask you guys in the exam situation or even with the proof. Okay? So do take a look at these properties in your textbook. A full binary tree. A full binary tree of a height h has exactly 2 to the h-1 node. It's obvious. Full binary node. You have every level, you have full elements in it. So if you do the log of, it's quite obvious. 2 to the n-1 node. Numbering the node in the full binary tree, we looked at it. The way they suggest is level from top to bottom. Also each level left to right. So 1, 2, 3, 4, 5, 6. That's the rule they proposed for numbering elements in the full binary tree. We looked at it, right? And then what else we looked at it? How do you find the number of your left child and right child, right? It's quite obvious. Like I think left child was what? 뭐였냐? I divide by 2, take the floor. If it's a right child, I would like to know right child. Number of my right child is 2 times I, is it? 2 times I. Of course, you have to check that whether those numbers you have, you calculated whether those numbers are more than the total number of elements in the tree. If it is, then it's not right, right? If it is, then you don't have right tree or left node or right node. 아, 오늘 이상하다 나도. So that was a condition you should check every time you try to find this. What is so good about having this type of numbering? What is the purpose? What do you think is the purpose of having this numbering from the beginning? Searching, maybe, yeah, searching too. Or we have a number by 1, 2, 3, 4, 5. We know the exact rule, exact policy of where things are. Maybe we can just store them in an array format, 1, 2, 3, 4, 5. Later, we can just look at the array. Instead of picturing this, just simply look at the link, array, and by looking at the position of each element, then we can find out where that element should be in this tree, right? Because we know how to number them from the beginning. 그죠? 1, 2, 3, 4 해줬으니까 그걸 그대로 어레이에 적어놓으면 나중에 어레이만 보고도 그 포지션 보면 그게 어디 붙어 있는지 알 수 있잖아요. 그죠? So this might be a good way to store elements in this tree. So if 2i plus 1 is greater than n, node I has no right child. So it gives you pretty much every condition to implement this tree on top of array. You just simply follow these conditions. If I give you a small pseudocode like the exams, maybe C or pseudocode, whatever, then I put a comment, put a condition for checking whether you have a right child or not. Whether or not you have a right child, then you should be able to put that as a condition, as a checking condition for that too. Okay, so be aware. We'll see what I can do. Complete binary tree with the n node. Start with the full binary tree that has at least n node. Number the node as described earlier. Top to bottom, left to right. The binary tree defined by the node number 1 through n is the n node complete binary tree. Binary tree defined by node number 1 through n. The n node complete binary tree. It's a complete binary tree. Everything has a number in it. So it has n number. That's a complete binary tree. A full binary tree is special case of a complete binary tree. Okay. See figure 11.7. 아이고. For complete binary tree examples, 11.8 incomplete binary tree examples. I forgot to put these figures in. So I will try to put these figures back in next class. I'm sorry. 내가 잊어버렸어. Okay. Do take a look at it. So I'm going to skip to the binary tree representation. How do you represent that into array and linked list representation? It's obvious. The next step should be how we can implement this into a computer programs, right? Obviously, we always take a look at two ways of doing this: array representation and linked list representation, right? Array, I mean, if you can number them, it might be nice. We can just put it in. Linked list, we all know how to draw that on the board, like giving the extra pointers. Maybe this time you can call it as a left, right tree. Maybe this time you might want to have a node like this. This is value. This pointer is for left. This pointer is for right. And whatever you choose to do, that might be the first thing you can come up with, right? And then you start adding in. Check out whether left place for the left pointer is null or not. If it's null, add new ones, just like one of these two will do it. In some cases, you might need to have extra pointers to go up, if you wish. I mean, if I have another pointer, like another element like this, value, this is a left of it, left, right. Say maybe it's a null. This one is also null. Then it's like this, right? Maybe in some cases you might need to go back up. I'd like to find out who's the ancestor of my stuff. Then you could come from the top again and count. Or if you're so lazy, then you can put another pointer here as 뭐라고 쓰면 좋을까? Parents? Maybe parents. Ooh. This one also have parents. But this one is pointing null. Is it a good way? I don't know. It's up to you. People like me so lazy just put an extra pointer in it just simply because I don't want to go over the entire tree one more time. Okay. So if I given you this as your structure for your tree implementation using linked list, and then I ask you to write a search function using this pointer, this format, then you should be able to give me some solution to it. Exploring this node, which means just following this pointer in it. So what else can you do? 프로그램 짤 때 이거 하는 거야. 프로그램 어사이먼트 주면 이걸 그려야지 프로그램을 짤 거 아니에요, 그죠? 그죠? 어떻게 해? 뭐가 맞는 방법인지는 모릅니다. 어떤 사람들은 포인터를 좀 적게 쓰고 할 수도 있을 거고, 그거는 뭐 자기 편한 대로 할 수 있는 거고. 또 뭐 다르게 할 수 있는 방법이 있을까? pair, array로는 이제 나올 거고, linked list 하면 되고. 또 다른 게 뭐가 있을까? 책에 없는 other than array or linked list way of doing it. Maybe, yeah. Skip list. I mean, oh, skip. Okay, then this one is, maybe this is a root. Left. This pointer is right, maybe. Yeah, that's good too. I don't know how to draw it. You wanna come and draw it? Yeah, that might be a good choice too. Just be careful to skip thing. If you're dealing with a small number of elements, then it's easier to keep track things in your brain. But if you're dealing with like 100 nodes, then you might get confused at the point. But a skip list is also a good example. I mean, it's not so much different from if you put this linked list into this linear format, then it's most likely a skip list like. 그래요, skip list를 할 수도 있겠다. 그럼 계속 포인트만 늘어나겠죠? 포인터가 늘어나면 어떻게 될까? If you keep adding a pointer to a pointer, what are the consequences of having your data structure like this? We will get large. Also, later you forgot what pointers do you have in your data structures. A bit confused. So be careful when you're using it, when you do it like this. But at least once, I recommend you do it like this too. I mean, you have the experience, so you will never do this again. Okay. So that's good. Skip list. 딴 거는 뭐 또 나오겠지? We'll see. Array representation of the binary tree. The binary tree is represented in the array by storing each element at array positions. Obvious? But what seems to be a problem here? That's a very dumb problem. When we number these elements for this full binary trees, we start from 1, right? The array we usually index by 0. Right? So that might be one thing to look out. So if you take a look at this one, then A starting from position 1, you have an empty spot at 0. So when you actually do a programming, you need to be a bit careful. Otherwise, you're starting from one position off. So everything else will be mixed up. Plus, it will be easier to compute your left child and right child if you start from 1. 0부터 하면 0 곱하기 2 하면 0. 이렇게 돼버리니까 귀찮죠. 그런 체킹 컨디션 넣어야 되는데. You could still do it though. So let me read it again. Binary tree is represented in array by storing each element in array position corresponding to a number assigned to it. A, B2. A's left child, right child. B's left child, right child. C's left child, right child. It has a rule to it. So if you want to do it in skip list way, then I guess if you want to add edges like this, then you use a skip list. skip list 하면 쓸데없는 포인터가 너무 많아지긴 하겠다. 그죠? 굳이 없어도 될 만한. But if you wanted to modify some of the skip list definitions, I'm sure you can still do it too. Okay. 이거 make sense 하지? 아, 11.8이 여기 있구나. Incomplete binary trees 1, 3 슬라이드가 바뀌었다. I'm gonna come back to this again. It's the same stuff. I mean 1, 2, 3, 4. Just looking at these two examples, if you have A, B, C, incomplete binary tree, again, A, C. What do you see? There will be a lot of holes in it. I will come back to this incomplete and complete tree anyways, but you can see the problem of having a lot of empty spaces later. 그죠? Array로 하면 one of the major problem will come if your tree is not full or incomplete tree, which is you're missing an element in each level, so you still have it, but then you will have a lot of empty spaces in array, which we don't want it to have. In terms of space complexity, right? Space complexity, we always want it to have a smaller amount of memory usage as well. Right-skewed binary tree. Right-skewed. It's probably not familiar with the term, but if you look at that picture, right-skewed. Right-skewed. Left-skewed. 한쪽으로 쏠린 거 얘기하는 거야. 한쪽으로 쏠린 거. Left-skewed. 이렇게. Left-skewed. In this extreme cases, you are wasting a lot of what? Spaces. 이렇게 하면, I guess if you're dealing with the right-skewed binary trees, then might be nice to use a linked list or chain to do this, or skip list랑 똑같은 얘기니까 I'm not gonna say it. But a node, a binary tree needs an array whose length is between n plus 1 and 2 to the n. Binary tree need array length of between n plus 1 and 2 to the n. Yeah. So if you don't know which tree you're dealing with, but you only know the height of the tree, what's going to be, then the maximum number of arrays you should define is 2 to the h minus 1, right? That's how much you need, or in minimum cases, n plus 1 node in it. So right-skewed binary tree wastes more space. What about left-skewed binary tree? Left-skewed는 어떻게 되나? It's pretty much the same thing, but still wasting a lot of empty spaces right there. Okay, when we number this full binary tree, they start from 1, 2, 3, 4. It's a bit convenient if you wanted to compute left child, right child. If you start from 0, 0 times 2 is 0. 그죠? 0 divided by 2. 0 divided by 2 is also 0. So they wanted to remove those special cases, so they empty those places. But that implementation is particularly on this textbook. You could start from a 0 and add some special checking conditions too. 귀찮으니까 책에서는 그냥 1부터 해갖고 앞에 비워놓은 거예요. 그러면 뭐 계산하기가 좀 편하니까, 귀찮으니까. Blame book, not me. Blame the book, not me. Most popular way, linked list representation of the binary tree is the most popular way to represent a binary tree. I mean, naturally, if you look at those array examples, there will be a lot of wasted spaces because we don't know what the trees will look like. In some cases, like his question was, if you have no idea how many elements will be in the tree, then what are you going to do? So to be safe, sometimes people declare very, very large array. So it's not very convenient, but not very smart. So that's why I say linked list way of implementing the tree might be a better idea. As it comes, we can add it in. Less space, easier to practice. And easier to do a visualization too. I mean, all the data structures that we do, drawing graph, it's much more clear than reading the text. 그죠? 모든 데이터 스트럭처 지금까지 나온 스택도 그렇고 큐도 그렇고 뭐 나왔던 모든 스택 스킵 리스트도 그렇고 아마 those things I don't think anyone remembers their definition in words. You guys probably remember how they look like in the data structure. 그림을 기억하지 아마 정의 그 말로 된 정의를 기억하는 사람들은 그렇게 많지 않을 거예요, 그죠? So linked list, it's much easier to represent the tree. I mean, it's very similar looking. So in the exam questions also, if you can draw these diagrams like this, then you are almost done. I mean, only things are left to is probably translate this figure into a pseudocode or function calls. So nothing much there. So it's like an IQ test. Use your brain, IQ test. 여기에 3D를 넣으면 어떻게 될까? 뒤쪽에 하나 더 여기다 포인트 하나 더 넣어가지고 100 이래갖고 이렇게 되는 게 되겠죠. 그럼 머리 깨지기 시작하는 거죠. 그럴 필요도 없고. I mean, if you want to make it really, really difficult, then those are the ways of doing it. Each element is represented by a node, has a two link field, left child and right child, plus an element field. Element, I call it as a the value, but elements, left child, right child. And I just added in parents just for my own use, just in case. And each binary tree node is represented as object whose data type is binary tree node. So you declare a node name as binary tree, new binary tree node. Okay. So when you try to create the binary tree, the first node that you're creating is probably root. So create one. The space required by n node binary tree is n times size of the binary tree node. What does that mean? If I need a n elements tree using linked list, it says n times size of the binary tree node. I have to include whatever element is, let's say element is character. Character is, how many bytes in character? 1 byte. 아닌가? 1 아니야? 1 byte. 깜짝이야. 2가 뭐가 있었는데 잊어버렸어. 그 우리 예제에 2가 있었다. 예제에 2가 있어서 아마 헷갈릴까. Okay. Integer. Let's make it integer. Integer. 4 bytes. Pointer, size of the pointer, size of the pointer. Then you add, let's say pointer is 2 bytes. Then 4 plus 2 plus 2, 8. For a single node, you need n elements in it. So n times 8 will be your space requirement for this tree, which will be much less. Imagine your array, integer array, single spot, 4 bytes, but you don't know how many elements will come, so you just declare array size of 100. That will be 400 bytes, right? Much less. So their way of drawing it this way. So when you're pointing to something, it means what? Pointers pointing to where? The return value of those pointers. It says pointing to this. What is it pointing to? 여기 포인터가 가리키고 있는 게 뭐야? So they will return memory address. Where is in the memory this B exists? Things that I exist. So I just follow the memory address of this element that I created. 그죠? And then if I wanted to find where's my left one, I look at this pointer giving me the address of here. So I just keep doing that. So it's not so much different from what I draw there as well. easy. 다음부터는 이거를 하나에 다 해야 되겠다. 귀찮다. 설명하기조차 귀찮은 챕터가 나올 줄이야. 그렇지 않아요? 그렇게 생각 안 해? 모든 챕터가 처음에는 좀 생소했으니까 그냥 한두 개 정도 했는데 그 다음부터는 첫 시간에 이거 하나 그리면 땡 아니야? 아니야? 땡이에요. 그림 하나씩 그리면 스택. Good. Q. Front, rear. Good. Done. 뭐 stack, pop, DQ, InQ, those stuff done. 그림 하나로 챕터 하나가 끝나는 사실 그것도 아니고 저것도 아니고 다 끝이지 뭐. 그렇죠? 이거 하기 위해서 제일 처음에 체인 가르쳐주고 막 이랬던 거예요. 체인 가르쳐주고 어레이 가르쳐주고. 그래서 사실 굉장히 쉬운 책이에요. 굉장히 쉬운 책이에요. 괜히 어렵게 만들어 놓은 것처럼 책만 크게 해놨지. 우리 때는 책도 없었어. 책도 없이 교수님이 들어와서 그려주는 거 보고 아 이러고 나중에 책도 못 찾아갖고 그러고 그랬던 것 같아. Node class for linked binary tree template class T. Okay. So they define in binary tree node the elements there in this way. Private T elements where I store my value. Pointer to it. 이거 pointer. If you have this pointer to the left child and right child. Public 3 constructors. If I create my node, if I create my elements, what might be the initial value of left and right child? Has to be null, right? No. If I started having my left and right, I would change the pointer at that location. So when I create one, left, right child, null. The binary tree node, T elements parameter only. So I'm gonna put the value for this binary tree node, given whatever I give, maybe I can put it as 1. Element is 1, left child, right child, null. At this point, I just give a value to this element. 그 두 가지 방법으로 그냥 하는 거예요. 그냥 이렇게 콜하면 바깥에서 저 binary tree 노드를 쓰려고 하면 binary tree node 이렇게 하면 I create empty one, no parent. No values in, I don't know what's going to be in. Left child, right child, no, done. The next one, if I use the next function, binary tree. 하긴 이렇게 코드는 한 번도 안 했지. 1. If I do this, then I'll put the value for 1, like this. Or A. That's what it means. That's just telling you how to use it. Binary tree node. At this point, it's obvious that you can give another parameter. So you can give a value for this element, as well as the binary tree node left and right. At this point, you can give what's going to be my left child and right child. So binary tree node. 아이고 귀찮아. Binary tree node B A. Let's see. I'm gonna call this as a tree node A. Big A. It's going to be my left. I could say no. I don't know what's going to be my left child. So these 3 different classes, 3 different ways of doing it is possible. That's what I mean by translating, understanding this to actually using a code. Okay. 3 가지 방법을 할 수 있다 이렇게 보여주는 거예요. 뭐 어렵지 않죠? 이렇게 쓰는 거나 저렇게 쓰는 거나 똑같은 얘기예요. 사실 책에 있는 코드가 사실 이렇게 난 마음에 들진 않아요. 괜히 막 템플릿 T 막 이렇게 써놓고 되게 복잡하게 해놨는데 굳이 그렇게까지 할 필요 없고 그냥 그래도 이렇게 아마 이걸 이렇게 봤을 때 이걸 어떻게 봐야 되는지 모르는 사람들도 좀 있었을 것 같은데 맞아? 아니면 다 알아? 혹시 모르는 사람들도 있었을 것 같은데 근데 이게 그 뜻이에요. 퍼블릭이라고 돼 있잖아. 외모 나올 때 퍼블릭은 내가 이 노드를 쓰고 싶을 때 쓰는 방법을 이렇게 가르쳐 준 거야. 네가 이렇게 3 가지 방법으로 콜을 해서 쓸 수 있다. 한번 부르면 이렇게 해라 라고 얘기를 하는 거예요. 예를 들어 내가 10개의 empty binary tree 노드를 만들고 싶다 그러면 for loop 돌리는 거지. for I equal 0, I less than 10, call this. Then what are you doing? You're creating this everywhere. You don't know where things are. 그렇게 해버리면 예를 들어 이렇게 해갖고 for loop I 0, I 10, I plus plus 이걸 없고 이 안에 이렇게 해놓으면 계속 비어있는 거 아무데나 만드는 거예요. 이렇게 만들고 나면 어디다 만드는지 몰라서 못 찾아가겠죠, 그죠? 만들 때마다 뭐 이렇게도 해주면 찾아가는 거고. So I can give you this, and then I can ask you to create a binary tree node having it like this. Or right child. Or right child. First thing that maybe outside the for loop, I create a root for you, and I tell you attach 10 right child using a for loop. 그럼 어떻게 해? 매번 여기서 만들어주는 거 이렇게 넣어주면 되겠죠? 여기다가 right child가 여기 있다, 여기 있다, 여기 있다. 그렇게 넣어주면 저렇게도 만들 수 있겠죠? 아니면 뭐 이렇게도 하든가. That's what it means. That's what it means to have a public stuff. 난 다 알 거라 생각해서 이런 걸 설명 안 했는데 알잖아. 숙제 보면 다 알잖아. 아니 우리 과목 말고 다른 과목에서 가르칠 때 안다고 얘기해줘. 아 그런가? 아 근데 뭐 클래스라고 하죠 뭐야? 우리가 맨날 얘기하는 게 뭐 저 네모가 클래스야. 이 클래스. 클래스 안에서 쓸 수 있는 펑션들. 우리 ADT 매 챕터마다 나오는 거 보면은 거기 첫 줄에 나오는 게 이게 하나가 이제 한 줄로 되어 있는 거지. 바이너리 트리 노드. 갖고 요게 안 나왔었던 거고. 그 아래 보면 퍼블릭 펑션을 쓸 수 있는 게 무슨 뭐야? add, delete, remove 뭐 이런 거 있었잖아. queue, pop. 그게 요거를 이용해서 할 수 있는 방법들을 했던 거. 그래. 클래스가 그런 뜻이에요. 이 클래스 하나, 클래스 하나. 몰라. 나도 요즘에 잘 안 해서. C는 때려친 지 오래돼서. 랭귀지 배우기 귀찮지? 그럼 파이썬을 해. 파이썬이나 루비를 해. 파이썬이나 루비. 그럼 뭐 클래스니 뭐니 이런 거 알 필요도 없어. 대충 쓰면 다 돼요. 이렇게 하면 메모리를 할 때마다 계속 만들어주고 지워주고 이러면 골치 아파. 나중에 내가 몇 개 만들었는지 어디 있는지 찾을 수 없어. 예를 들어 저 포인터가 중간에 끊긴다고 내가 표현을 하잖아. 이게 넣다가 실수하고 잘못 넣는 거야. 그러면은 저 뒤에 있는 애들은 메모리 어디 있는지 찾을 방법이 없어. 그러다가 이제 블루 스크린 뜨는 거예요. 메모리 꽉 채워가지고. 근데 파이썬 같은 거는 뭐 그럴 일 없으니까. 자바 같은 거는 그럴 일 없어요. 자바는 알아서 지워주기도 하니까. 근데 C나 C++ 하는 사람들은 저런 걸 주의를 해야죠. Common binary tree operations. Determine the height. Common binary tree operations. So it's like a settable operations for ADT. Determine the height of a tree. So I have this, giving you this class, and then I would give you write find height function. What do? What do you do? How do you write this? Yeah, maybe dumbest way you can do. You know where root are because I'm giving you the tree. Giving the tree, I give you the root where the root node is, and I want you to write a finding height of the tree. Maybe you go all the way. What does it mean to go all the way? 저거 어떻게 적어? 코드로 적으면 since we discussing in code. 제기? Okay, that's also too recursive is a way of doing it, but there is an easier way. Why do you use a recursive way of doing it? Maybe, let's say I'm going to call as a root as this node. So I'm going to declare some temp node, temporary node, like this, while I'm going to say temp is root, something like this. While my temp is not null, the temp, of course there should be other condition, temp to left. 이런 식으로 계속. If I keep doing this, I'm going to ask, this will be the temp, the name temp. I'm pointing to the next left one as a temp again. Temp, keep going down. While I'm doing this, maybe I do a count plus plus. 그러면 when I'm done, of course there should be other conditions to check whether your node is empty or not. Then later you print count. Well, then it might return me return me total height. And recursive, what you mean by, because you don't know which one is like this or not, then you should use a recursive. I was referring to just one way. Tree like this. 예를 들면 리커시브가 맞긴 맞아. 왜냐하면 이 안에서 또 뭐가 변해가지고 더 아래로 내려가는 애들이 있을 수도 있잖아요. 그런 경우에 리커시브를 쓰는 게 맞고 이걸 리커시브 부르는 게 맞는데, 예를 들어 뭐 한 줄로 된 트리 같은 거 볼 때는 뭐 이런 식으로 해서 쭉 따라 내려가면 돼요. 계속 포인터 따라 내려가서 제일 끝까지 가는 애들. 그러니까 여기에 대해서도 한번 이걸 해보고, 여기에 대해서도 이걸 해보고, 여기에 대해서도 이걸 해보고 해서 가장 큰 숫자가 나오는 놈이 화이트. 그렇게 한다거나. 이제 그렇게 잘라 그러면 리커시브를 하는 게 맞아요. 근데 예를 들면 이런 식으로 간단하게 할 수 있다 이거예요. 뭐 별게 아니라고. 포인터를 따라간다는 의미가 그냥 이렇게 따라간다는 뜻이에요. 내 다음 포인터는 얘니까 얘부터 다시 시작해서 더하기. 아주 단순한 예예요. 이렇게 짜면 100% 세그멘테이션 폴트 납니다. 실제 프로그램에서 이렇게 짜면 컨디션들이 많고 전체 하이트를 해줄 수도 없고. 그렇죠? 하나 예제예요. 이게 맞는 건 아니야. 예제예요. Determine the height, determine the number of node. Determine the number of node. Well, you can also do the recursive, always recursive ways to want to go. Follow all the pointers if you wish. Follow on the pointers and count one. Or if it's an array-based one, it's much simpler. Make a copy. How do you copy a tree? 저것도 그러네. In some cases, I guess array is better. I mean, if you want to copy those trees, then you have to explore every single node in the tree and then do it yourselves. Do one copy at a time. Determine if two binary trees are identical. Wow, it's getting difficult. How do you write a code to? I'm giving you two binary tree and asking you whether those two trees are equal. How do you write that? How do you write that? 어떻게 하면 되나? Yeah, maybe. You want to translate your linked list into array format, and then you might want to compare two arrays later. Probably the dumbest way you can do. Easiest way though. If you don't have any memory requirements, you don't care about the operation cost, then that's also a way to do it. Display binary tree. So why are we going over this? They were gonna give you the way of how to read the tree. Which order should we look at the tree so we can compare, copy, or determine the height, like that. If it's an expression tree, evaluate the expression. If we use a tree to store a formula, a simple plus minus division formula, whether that is a right tree to store those informations. If it's expression tree, again, obtain parenthesis form of the expressions. If it's a formula, if you use a parenthesis, which one you should compute the first, and then you're giving an order to a formula. So in order to do this all kind of common binary tree, they usually give you the way of how to read your tree, which is also called as traverse a tree. Simple word is walk around the tree. Which way I should go first if I'm giving a tree? Should I go left first, right first to print the value? Let's see. And many binary tree operations are done by performing traversal of a binary tree. You walk around the tree and compare. If you try to compare a two binary tree, whether they're equal or not, if I traverse the tree in the same order, then the element should be in the same order too. If I go left, then left element should be identical to the tree that I'm comparing to, like those. In a traverse, each element of a binary tree is visited exactly once. You do it once, you go there once, you never come back to this node again. Traverse the tree. During visit of an element, all actions make a copy, display, evaluate operators with respect to this element are taken. Every time in that element, whatever I do, it should be done. Copy, display, print the value of this node. It should be done when I'm in here. Okay. 뭐 되게 어려운 것 같이 설명했는데 it's a very simple way of doing it. They actually give 4 different way of reading your tree traversal method. Pre-order, pre-in order, post-order, level order. So easy, it's nothing much. If you take a look at that red font, root, left, right. The way of reading my tree is root, left, right. Again, it will be my, okay, I'll come back to this. Root of a subtree is processed first before going into left, then right subtree. In order, after complete processing of the left subtree, root is processed followed by processing the complete right tree. Left first, root, and then right. Okay? Left, root, right. Post-order, the root is processed only after complete processing of left, right, and then root. Left, right, root. So 3 different ways of reading, traversing the tree. Example is much more simpler. Level order, the tree is processed by levels. Level 1, level 2, level 3, you read the elements in that order. So first on the node on the level I are processed from left to right before the first node of level I plus 1 is visited. Level 1, level 2, left to right. Level 3, left to right. Example is much simpler. I'm going to come back to this. For the pre-order traversal code, this is a recursive way of doing it, and we'll take a look. But let's take a look at the example first. How do you read this as a pre-order traversal method? If I wanted to print out the elements in the tree in pre-order, what might be the outcome? It was what? It was root, left, right. 그죠? 뭐겠어? You guys have a solution in your slide anyways. Let's see. A is a root, A. Left of A is B. And then root, left, right. Root, it's a root of B, will be left again, D. D's another root, D's left is G. So I'm gonna go to the left first. A, B, D, G. Every time I do a root left, root left, root left. And then I'm going to root left, right. So I'm going to go right. Next one will be after G, I'm gonna go H because that's my right. After H, I'm gonna have to go B's right, E, and then C. And then I will just do the same, root, left, right, root, left, right. Root, left, I don't have a left, C, J, this way. Root, left, right, recursive way. Recursive way. 이렇게 크게 시작을 해서 루트에서 레프트를 봤죠? 이렇게 다시 보면 레프트 먼저 봐야 되니까 크게 해서 레프트를 먼저 봐야 되니까 이 레프트 안 해본 것도 다시 트리죠. 이 안에서 다시 레프트 먼저 보고 크죠? 다시 트리죠. 이 안에서 레프트 다시 보고 그리고 이제 없으니까 right 보고 right 보고 right 보고 큰 게 이만큼 남았지? 다시 left 보고 이건 left 없어. 그 right 보고. Order you read that pre-order. Order of the elements in pre-order way. A, B, D, G, E, I, C, F, G. It's a recursive way of doing it. 저렇게 읽으면 어떻게 돼? 저렇게 읽는가 보지. 그죠? So they will tell you which way they read your trees. And they don't mix it up. So they probably give you the way of reading this tree is pre-order. What's going to be the output? Okay. It's a previous slide. If you actually try to write that as a code, this is my pre-order function. Giving the node t, this will be my starting node, root. If t is not null, I'm checking whether the root that I'm given is empty or not. If it's not null, visit t first. Visit t means visit t. T here. First. Okay. And then I'm gonna explore the left of the tree. When I visit, probably inside this visit function, I probably print out the value of the t. Print t, same as. Left, I need to look at the left first. So t's left child, this. I'm gonna call again for the pre-order here. That's why I call the same function inside the same function. Pre-order left first. Root, left, right. In terms of coding, quite simple. We only need 3 lines of code printing out. So when you actually call the pre-order t left, it will be called again with the left child of the t. If it's not empty, they probably print out the value of a new t left. 그죠? And then they're gonna call another pre-order up here. When they actually go into that, they also print out the value of this one, check whether they have a left or right node, and do the same thing. So that's a code for having this pre-order representing an element in it. So it's quite obvious for the post-order and in-order. So you probably switch around the sentences. 이제 이것만 슬슬 바꿔주면 되겠지? Based on the root, left, right. 또 뭐였지? Left, root, right. 그죠? Left, right, root. 그죠? Very similar way of doing it too. 아, 여기 써놨구나. Visit as a print. Sorry. Visit as a print. Visit as a print. So that's what I'm going to do at the end. So if I ask you the similar coding question, write a code for pre-order traversal for your trees, binary trees. So simple, right? You only need 3 lines. If you can remember that, then you will probably try something like this. It's probably quite difficult to get the right answer for this. 아마 리커시브가 생각이 안 나는 사람들은 막 이런 식으로 해보려고 막 while 쓰고 막 이럴 텐데 잘 안 될 거예요 아마. 복잡해지면 잘 안 될 거예요. 뭐 예를 들어 내가 이거는 full binary tree다 이런 조건을 주지 않는 이상에는 이걸 하기에는 쉽지 않을 거예요. 쉽지? 됐지? done? 뭐 어려울 게 뭐가 있어? 이게 뭐야? So expression tree, forget about the pre-order expression. Expression tree that we looked at before, they usually do this way. It's in the middle, left, A plus B times C minus D divided by E plus F. That was a typical way of looking at expression tree, right? So it makes sense, look like a formula. But what if I did a pre-order way of reading that expression tree? 그럼 어떻게 돼? Give me the answers. Just call out the answers in your slide. 거기 답 있잖아. 없어? So root left right, root division left star the multiplication that of left is plus 맞나? And then A, B minus CD plus E and F. Boo. Doesn't look like a right formula, but in the pre-order way of traversing a tree, this is right way of doing it. Gives a prefix of the form of the expression. Forget about that. It's okay. In order. 뭐 이제는 뭐 똑같죠? In order. It seems to be doing on the left first. Left child first, visit T, and then root in order T right child. 만약에 내가 이걸 기말고사에 물어봤는데 이걸 틀린다. 그러면은 문제가 있는 거야. 그죠? 이거 리커시브가 뭔지 몰라도 때려 맞춰서라도 할 수 있는 거니까. 그죠? 내가 뭐 리커시브를 뭘 깊게 알라는 것도 아니고 대충 어떻게 써먹어보라는 거니까. So if I do a visit for this in order visit 뭐였어? 나도 까먹었다. Left first. Left root right. So left 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 from A left again left left. When I hit G there will be no left. So I visit G first. Print G first. G root. G's root is D. 맞나? D? 맞구나. D. And then right, H. So you can now see the pattern of a smaller part, and then big picture. So if you look at it as a big picture, no one break a rule of left root right, left root right. 전체적으로는 그게 큰 트리에서 왼쪽 거 먼저 보고 위에 거 보고 오른쪽 거 보고 그 룰이 깨지지 않죠? 계속 내려갈수록. 그렇죠? 그 룰이 깨지면 이제 리커시브가 아닌 거지. 뭐 잘못된 거지. G, D, H, B, E, I, A. At that point, that I just cover all the thing on my left side. That's why I hit A as a root. F, 뭐야? F, G, left, right. Yeah, F, J, C. F, J, C. Even though it looks quite simple, I recommend you to practice at least once. Just write it down. 나중에 later you will get mixed up some point. I mean 하다가 나중에 시험 쓰라 그러면 꼭 헷갈려 갑자기. 그러니까 손으로 한 번씩 이렇게 써봐요. 오래 걸리는 건 아니니까 한두 번 해보면 안 헷갈려요. In order by projection. Actually, in other way of doing it, you actually did actually this way. 그죠? In order 이렇게 하면 그냥 아래에 있는 거 그대로 내리는 거랑 똑같아져 버리죠. If I do this on an expression tree, it would probably look like a right formula. 그죠? expression tree in order로 하면 비슷해 보이겠죠? Like these ones. pre-order, if I do a pre-order way of traversing on the same tree, they look weird, but if I do an in-order reading, it sounds like a good formula, A plus B times C minus D divided by E plus F. 맞지? 아닌가? 맞지? I will discuss further for this infix and parenthesis later. Let me see. I'm gonna take a look at this post-order traverse. 이것도 뭐 뻔하고 left, right, root. 그죠? There isn't too much different from and the previous ones. So I'll continue to discuss on this pictures, including full binary, incomplete tree, complete trees, as well as infix parentheses, adding a parenthesis as well next class. 질문.